introduce Oleksandr. Where do you work now? I forget where you work.
Facebook. Yeah.
Yes. Oleksandr's at Facebook and taught at PyData last year, and will give us something about information surprise this morning. So let's welcome Oleksandr.
Thank you. So I prefer to talk about simple things that actually make difference, and people often forget it. Everybody's right now runs and measures how many control parameters their systems have and their machine learning pipelines. But actually, all we should remember is our bachelor degrees to do most of the stuff. So I'll be talking about surprise, which is turned out simple. And what is a surprise? It's actually something that really puts you off, let's say so. And if we just go into definition of surprise, and well, here I'm borrowing one from Oxford's dictionary, it's a piece of news unexpected that it happened so suddenly. Like actually, some things that you didn't appreciate, well, at the moment when it happened. And we will be capturing these events in order to describe tweets in this demo. But in general, I want to, first of all, introduce all those things through toy cartoons and actually some theory. So when cat explores and it just goes around your garden, all it sees pots of your flowers, but it's nothing that surprises a cat. He sees it every day. And well, suddenly something very odd happens. And that actually really puts him off. And this is a moment of surprise. And clearly, we can see that surprise measured in volts. And this is actually even cited in scientific papers. We've seen that everywhere. So how to quantify it? It's a proxy measure for this will be complexity. That can measure any content type, which wouldn't be tied to anything specific. Very important note here is that complex things aren't random. And this is a slide out of one of the papers which actually using similar information theory techniques to analyze music. And they were showing that good music, just right, it's not deterministic, which is like repeating beat, and it's not completely random. And it's very hard to find the sweet spot, and they were looking into this. But if you just look quite broader, all measures of complexity, well, there is like a whole family of them. It's very subjective. It's like a cat, whatever cat thinks. Or it's just some numbers, number of elements, dimensions in your system, control parameters that we love to calculate, minimal description, if we'll to archive something, information contents will be after here, minimal generator, if you heard about Kolmogorov complexity, if you can write the shortest program to generate the sequence, or minimum energy principle. Surprise quants in academia is actually, well, I'll like to split them in two parts. One of them is like cognitive sciences, and they study how do we perceive information. And it's very interesting for us because at the end of the day, we want to find something that's actually interesting for people, interesting for human beings when you analyze massive data sets. And there is machine learning, and they are more interested in applied things, how to measure things and how to measure differences, because that's how we code things. Nice things that actually they are play with each other. So if we'll take a look, for example, in a review paper on cognitive science, they put lots of models which are very analytical, and they are built on very simple and similar to information theory, some of them concepts, including, for example, in middle, just about free energy, there is a Bayesian brain hypothesis, quite popular one. In machine learning, where we have this application, they said to transform something for human being or also in optimization. This is an example back from, I believe, beginning of 2000s or even 90s, when people at Microsoft were building the first routing system, and they wanted this routing system to tell the driver only unexpected events. For example, you every day have traffic on your road, but today it's completely bad. You won't be able to pass it through. So the system had to build a model, detect it, and only report surpriseful information without spamming you. So all these things that I told you, they're combined. And there are studies that are showing that the way how we, on images and videos, define interesting bits of information and what we can learn through these approaches, not exactly entropy, but surprise approaches, are very similar. and we will define the same bits of information in video stream, for example. Core principle is very simple. Should we have pictures that it doesn't change, and between our prior and posterior is very little difference, nothing happens. Should we just swap for random noise? It's a big event, and clearly you would be caught by surprise when you'll be watching a video. But in some time you'll be turning channel off. It's not that interesting for you anymore. In ML, it's a bit different. It's all about optimization. It's about decision trees, max entropy principle. All we know about this is called basically anomaly detection, or one-class classification or novelty measures. There are quite a few different approaches: probabilistic, distance, domain-specific, domain-based, reconstruction-based, information theoretic. But, well, I bet all of us came across with all these problems, especially when we were logging something, we're trying to detect where something broke and to report to. But let's go to the cat. So the cat has his data, his garden. He has tiny attention span, only one pot. And he has his own brain trying to model what actually to expect from the world. And this builds his surprise, whether he's seeing the plant he was okay with, which were there yesterday and the day before, ignores it, or finds something interesting. While doing so, he updates his data model. It's similar to anomaly detection pipelines. So focus on surprising bits information theory. And to quantify surprisal, it's back to your bachelor's degree. It's some measure that is about 0, but if we exactly know that the event had happened, it's equal to 1, and it's in range of probabilities. Events of different states, like pods or astronauts, are independent. And we're deriving, what do we know? Self-information. And what we know is that flip a fair coin gives you exactly 1 bit of information. And bit, it's exactly this part. It's log-based too. And should be seeing something very expected, our self-information goes to 0. Should we see something completely unexpected, it will go to infinity. Because, well, seeing an astronaut in the garden. It has applications, and one of the applications, for example, in selecting information source. Sure, you might be after very random information source, but should you be behaving in a society which sensible? It allows you to organize better ways to propagate information in network societies. It's actually part of my studies I've been doing in Southampton a while ago. It's not only concerned about this, it's about more emergent behavior, which patterns emerge on large scale when agents or people behave so. But it's clearly information surprise was showed to be, I've been showing that it's one of the driving factors to have beneficial society organization. So if we'll go back to model of a cat and think about his knowledge, what he knows about the world, he knows about pods and astronauts, and quantify his knowledge, it's what we know self-information, expected value of self-information as entropy, Shannon entropy. It's basically about all terms, we summon them together. And maximum value will be if all events are equal. And minimum value will be of entropy if only one event is known. So basically nothing surpriseful. It's always the same, I see the pods. Or I don't know what I'll see, and that is surpriseful. The maximum is least informative, and yeah, it's basically a uniform distribution. And nice bit, the statistical mechanic has clear link information theory on these terms. Where we can apply this, it's one of the nice examples, which is actually very visual and people love it. It's analyzing binaries. When you give an unknown binary and you want really to dive into, you can visualize with entropy. You can slice your binary into tiny windows, measure entropy of each window, and then suddenly you see, for example, this database on the later part, when it's more lower values, it's basically English text, having all labels for the cities, and the first parts, which are very fluctuating, these are matrices of different numbers. And sure, it depends on regularity of your matrix, whether it's high or low entropy value. The nice website on the internet called BNVs allows you to visualize binaries. Uploading binary, for example, this K-shell from OSX, and visualize an entropy view. And suddenly you see blocks. 2 blocks, like this number 3, are quite clearly just a list of all symbols, and they have the highest entropy because they are not repeating. And the other 2 turn out to be cryptographic signatures of the file which macOS builds in. Clearly, you can play with it. But more interesting, which we're after today, how to do discovery, how to find what has changed, how to combine all those things together. And the one I'll be talking here today is about measuring relative entropy, information gain, with using Kullback library divergence. I'm sorry for pronouncing. Let's short it to KL divergence as we know it. And it's a not though true measure. It's asymmetric. Given your prior and your observation, you have one outcome. But should you swap them around, you'll get another one. And to battle with that, you can actually build symmetrical distances. And as it was good to show that pretty much on analyzing text corpus, they give you very similar results, and they can be used interchangeably. So I'm just going for a simpler one that I'm measuring from my, it will be actually prior and my observation and back, and taking the maximum value. However, calculating KLD also gives you trouble when you are dealing with very sparse data observations. Clearly, some data bits might be missing, and if there is 0, it brings problems. So it's known as smoothing of KLD when actually we assign to all terms which are absent in one of the distributions to tiny, tiny value, and then normalize the rest to sum up to 1. So here is a comes demo application which I'll be talking about, finally. It's how to find surprise in tweets. And when we see tweets, we are overwhelmed, especially when we're following something big happening. And it's more about, can we detect events and annotate them in short fashion with those tweets? So, unfortunately, the data set is a bit gruesome, and I'll be showing you examples on data I've been collecting over the last year about Ukrainian events that happened back in my country. And so it wasn't that funny. First, side note, if you want to explore data sets and just look with your eyes on this scale, drop them into search engine, which allows you to do faceted search. I found Elasticsearch plus Kibana amazing. Yeah, but more about discovery. So this is a whole data set. It gives you data from December 2013 up to current point in time, where I still have hopes to find where left this partition. Yeah, this is lots of data, and I was been always running out of disk space in my node. Well, so what I have here, 75 billion tweets per minute on average, like 500 tweets. Per hour, it's a bit less, sure. And here is it per day. And you clearly see there is a regularity in this data set and something happened. If you remember, even like news on BBC, you may recognize some. For example, this strike, huge strike, is the crash of Malaysian airplane in east of Ukraine, which was shot. And there are others which are happening. And we were about to focus on that green one, which is experiment data set. And here is like, for comparison for you, when annexation of Crimea was happening and when presidential elections were happening. So this data set is massive in amounts of events that happened there. Following this as a human and reading it just drives you nuts. So if you're a data analyst, it actually this way of looking at it gives you some relaxed approach because you have a very bird's eye view. So this is experiment data set from February 2014. It has clearly 2 different stages when events were constantly happening, but they were kind of isolated to Ukraine, and then something big blasted out and it went really to the world news. Everybody wrote about it. So because it went to world news, clearly English language started dominating, especially in this last part of the month. So here is the English-only tweets, for example, which we're only going to analyze. I'm just going to filter out the rest. So how the pipeline looks in order to look into this? Just stream, then it looks at, we take a time slot, our attention windows we want to analyze. We will be comparing it against our prior, which consists out of 8 previous time slots. And we will be detecting, is it a new event or it's something to ignore? So how are we going to do it? How to calculate Kullback-Leibler divergence, Leibler divergence? It's clear, but we need somehow to prepare our data. And I'll want to show on purpose for me initially that even simplistic topic modeling do the work. We sometimes, we all know that tweets are super short and cannot be analyzed easily with NLP approaches. But we oversee how simple modeling bring us the results. So why it works? Because important events are widely discussed and we have lots of tweets. Events change vocabulary, so actually modeling events with simple back-of-word approach works. And time slot aggregations favors the predominant events, which is a negative thing. Should several events happen, I'll see only the predominant one. But since I'm taking tiny time slice every time, it's sort of okay. So here, if we will be talking in terms of NLP, document is a time slot, it's not a tweet. It's a bag of word of this time slot. It has a frequency threshold of in how many tweets each token has to appear in order to be considered. It's very naive term frequency, no normalization by inverse document frequency, and quite a few touches how to clean Twitter data because it requires so. Clear view on a vocabulary, which is kind of sort of power law. I'm not going to claim it. And we'll be focusing only on this tiny end, which actually covers most of the tweets. Here is the number of top tweets, which are top tokens in this data set, which are about Ukraine, retweet, Russia, Kyiv, president, protest, visa, via US crisis. Everybody's involved in it. So vocabulary diversity is the first thing. How many unique tokens we have? And as we've seen initially, we have 2 different parts in it. And sure, part when world media kicked in dominates. That bit run out of disk space actually is also nice to illustrate how metrics change when you have a gap in your data. So we can do very simple things. We can do vocabulary hack. Let's take all catastrophic wars. We describe these gruesome events and see where they are predominant, and those should correspond to events. Well, sort of they do, but they still kind of very regular and they follow the daily cycles. And we cannot really rely on that. We'll be just detecting it's a noon in Europe. So we're going to kill the divergence, and here showing you the simple approach that I'm taking each hour and comparing it the whole dictionary of the whole months in order to build up understanding. And we have higher values for KLD on sparse data, sure, because my prior, which is my distributions over tokens over the whole months, is huge. And here I'm comparing sparse bits of this only Ukrainian, Russian predominantly tweets. Beware, we have lots of spikes here, but there are lots of events happening. It's tiny hours in it. We'll dive a bit deeper later. Smoothing that I showed you before. In the previous slide, I was basically dropping pairs of tokens which didn't exist in one of the sets. Smoothing allows me to compare it in whole without drop out. And you see, because of the smoothing, minimum value jumps in. Pretty much on empty, if you compare empty time slot, it means that actually it's not empty. All tokens are equal to this tiny epsilon. And here I will be doing rolling KLD because comparing against the whole months it's not interesting. I need to compare what has changed in last time period in my model, which accounts last 24 hours, for example, in this case. I'm accumulating them. It will be my prior, and my tiny hour will be my observation. Nice thing is that as we shorten time slot, and for example, 8 hour, it's pretty much your day cycle, which covers all bumps of media coming in. We pretty much getting rid of all daily cycles. We end up only with spikes that were happening. With 4 hours, it's pretty much the same. So that's why I'm taking 8 hours. So now we need to do event detection. Again, let's do super simple. I want to show how information surprise works. I don't want to show how NLP works, either event detection works. I'm measuring only rate change of the surprise of this KLD value. And I'm comparing against the historic ground truths. This event touched lots of people put their effort, and somebody built a huge time slot manually, annotating every single event that happened. And this is immense amount of work. And that gives you something to compare against, which was amazing. So here's events were detected as a rate change. And here I'm annotating events with the most surprising tokens, like which tokens like really changed here. You don't need to read it, but the whole point that we see clearly here that something happened, clashes happened, then president ran away. Then there was interim president, the president basically head of the parliament, and Russian interventions, and well, US commenting on that. All the events are coming, but they are not descriptive. I'm not going to read tokens. It's a bit non-human. I want to understand what's in data. So let's focus on prime events because I can zoom in on it, and they have better English coverage. So here again, this is the same. We have here a bit more events, but it's kind of more smoother. How we're going to find representative tweet? Very simple, again. We have this time slot, and the upper part of the model is from my previous pipeline. And the first step, it detects distinct features, but instead of calculating the cumulative score by integrating all terms of KL divergence, we're leaving them in distribution and passing into second Hilbert-Lipper divergence. And this time, we comparing all tweets in my time slot against this bit, which was the most surprising between my time slot and my prior. And by doing so, I'm finding exactly these tweets which are representing distinct features. First of all, on first stage, I found tokens which are unique to this hour. And on second stage, I found tweets which are matching exactly these unique tokens. And this way I'm finding my toucan, which was hidden. And then I can visualize this in a simple demo. I'm not going to show you to scroll through all events. I'm just going to pick up a few screenshots here. And the first, I have to tell you, this data set on purpose hasn't been cleaned from the bots. This data set, at least 30% contains bots, because this was highly sensitive political topic, and Russian media was really working hard on it. And we having like this problem everywhere in all social media channels even up to now. I didn't clean them. I didn't clean from any regular Twitter bots. They can be all detected actually using a very similar entropy method because bots behave very differently. And should we capture bots' behavior? Are they repeating themselves? Are they acting one after another? And basically trying to describe their profile with entropic measures, they're different. I'm not doing this here. And so here we are. We see the first tweet being spam. Why is so? Because this is the first tweet actually in the hour. My prior is empty. It is actually all tokens being equal. And so it picks up pretty much the first tweet which was predominant by its mass in the first hour. The most surprising for me doing so that in all the rest of the tweets which were selected in this way, I don't see nobody from spammers. I don't see bots which were forcing the news and repeating the same tweet, which were hundreds of those in each hour. I see pretty much decent media. Example here. Intense clashes, riot police falling back, petrol bombs, tear gas, lots of smoke. It's went into media. So in this demo, I'm selecting one which has like this highest score in the second step, then few tweets which have like which follow it. Then I was testing a bit different metric, and then I selected the first tweet with the highest measure, which has media in it, in order to illustrate it. Sure, not always comes to good, and for example, here is a comparison. It's about related risk of disintegration when Russia was starting to press on Ukraine and Crimea, and other media comparing Ukraine to Venezuela, and this is a photo coming from Venezuela, but actually tweets is saying comparison to Ukraine, and I looked into that, and it turned out that media in that day, in that hour, were exactly comparing events in Ukraine and Venezuela, and they were in the same data set. And sure, Venezuela was very surpriseful to appear in mine. It was actually quite funny because I later found that media went, they confused themselves and they were illustrating Ukrainian events with Venezuelan pictures and vice versa. So then horrible things happened. There were like very serious clashes, people died. And this is our breaking news which very went, and there was a settlement of political crisis involving lots of parties discussion. And then president fleeing, old prime minister returns from capital from prison, what she was doing there. Then all talks of US and Russia involved. I'm not going to dive into like all those events or all those plentiful. Believe me, they are good and descriptive. And I've been checking against that ground truth. Sure, it's not perfect. There are lots of things to improve. But the takeout that it's not that bad. Right now, it's everything back to normal, and those gruesome pictures you saw, it's everything okay right now there. Well, the only building which has been burned is being revered. To improve in this app, we have to benchmark against media like more directly, because manual cannot really work on it. We need to fight with bots, because that will help us to do better topic modeling in return. It's not just term frequency. Tweets have to be treated very differently. And the later bit, we need to split topics, because at every point of time, we have lots of events happening. We are dealing with a complex database, which is not a single value of a rate. It's a combination of all events happening. But what's amazing with this simple approach is you can actually achieve quite a bit. And this was only takeout. Don't forget your bachelor studies. And before applying very fancy modern techniques, however good they are, just look very simple ones. Thank you. Well, I rushed through. I actually was very worried that I have too many slides. Yeah.
Oh, that was perfect.
Yeah.
It's half an hour.
Better for Ian.
So we have a few minutes for questions.
Sure.
I'm curious, like, how did you get the public Firefox or
No, I wrote a tiny. Sorry? Oh, sorry. I've been asked how I acquired the data set. It's not public. The only way official to acquire a data set is go to DataSwift or GNIP and pay quite a bit, especially for a long period of time because you have to scrape it. And I was doing a bit different. I wrote a tiny bot which is still listening to Twitter streaming API, which provides you a sample tweet when you subscribe by keywords. So there is a clear bias in my sample. I subscribed to a set of keywords which were representative for those events. And also Ukraine, Kiev, the revolution tweets, all my timer. All those basic in different languages in Ukrainian, Russian, and English. And this is how I acquired the data set. Despite it being sample, and Twitter does not disclose exactly the way how they sample it, I found it quite representative. It's much simpler than you think. It's very simple.
Just to know, DataSwift lost their Twitter deal, so it's GNIP and I think another provider for
DataSwift.
Swift.
DataSwift.
Oh no, DataSwift. Who are they?
They are based here in Reading. As far
No,
as
that's DataSwift.
DataSwift, I'm sorry.
And they lost their license with Twitter a few months ago, and they put up some slightly acrimonious blog posts saying, Twitter, we don't like you anymore. You didn't do a deal with us.
And didn't Twitter
They supply
acquire
lots of other
GNIP?
social data.
Yes.
They.
Yeah.
Oh well,
Yeah,
okay.
so
I
it's
guess
actually-
that's why that
getting-
happened.
This is reason for DataSwift to get
You
lost.
get lots of other data from DataSwift. Another question over there. Was that?
I would like to know what you think it would be advisable to do topic modeling, like latent models, using some kind of word-to-vec or some deep learning technique. What do you think will be more advisable? Because it's really not clear how you can model the topics of Twitter.
Sure. First of all, you will end up with a similar problem that after you'll model a topic, you'll have several different events happening. So you'll have several different clusters. You have to build on top of this tiny bit, which will be splitting your stream of data into substreams, because, well, this is quite an elaborate process. And before going into that, you have to figure out whether it's worth doing. Applying word-to-vec, because when I didn't do it, because when I first started playing with this, I listened to a presentation of word-to-vec, and it was said by the author, you should not be applying this to sentences or doing this very cautiously because it didn't work. Right now we know there is an extension to that which actually works for tweets, works for sentences, and nicely captures sentiments, the state of the art, but it's all developments. I highly encourage doing that, but this entertaining presentation shows that you don't need to do it. Not always.
Hi, out of curiosity, what applications did you have in mind for this study?
We currently continuing to working on this data set with my friend who is doing his postdoc in King's, and we are looking forward to publish statistic description of the data set, in particular how we are trying right now to differentiate how forced events on Twitter differ from organic events, and it's a very interesting problem. Can we actually early into Wave tell you that this is a forced opinion, which is a fake and has been forced by disguised bot network, or it's organic events which are reported by people. This is one of the things we're looking, because we have data set for that. Unfortunately, it is manually labeled. It's only hundreds of those fakes, and it's kind of hard to map it to our data set. We will get a statistical description. I'm not confident we'll have a proper classifier for that, which will have enough confidence to do it. This is one of the directions we're looking. We're considering other things, but I'm all open to discussion because we are sitting on this data and just poking into it.